Good morning, Adam. Thanks for the invitation. It's a pleasure to be here. Greetings, everyone. I'm Robert Bressan from Petrobras, as Adam said, and I currently work with digital solutions for Subsea, especially in change management. And my job today not only bringing insights on how computer vision improve digital tools, but vice versa. When we talk about maintenance and use the digital twins, we are usually interested in operations that have many maintenance operations throughout their lives. And we can associate behaviors of similar systems with the same model. In production units, we can have dozens of safety valves, control valves, about hundreds. No. Then, with all this information, the model starts getting shape quickly because of this immense amount of correlation. And when a scope of work is something that's absolutely expensive to replace and has very few correlations, like a white Christmas tree, the design of these entities is done so that maintenance is never carried throughout its service life. So there's not much material for learning these components. A wonderful way to gather this data is through testing. Laboratory test is our front row of getting insights on what's happening to our assets. And another great tool to use is simulation. When physics models are known, it's a great place to place those data. But did we miss something? Simulations take a great step, but there is some field data until there is some field data, we cannot be safe on our model. And in Subsea, this is where we become fragile. Basically, the information available on sets is some sensors at key points, you know, and some inspections at relatively long intervals, 4 to 5 times over the service life. Virtually all the information in these inspections is visual, obtained by ROV. This is even more critical when it uses subsea flexible pipes because there is very little reliable instrumentation for those. We don't have good sensors for these ones. So, how do we make a digital twin without that amount of data? It's worth thinking that, but everyone who did a self-life calculation by hand using a calculator did a digital twin, a primitive one, and instead of using as much as that as possible, use on the first point, the project position. All the remaining data was simply discarded. And it's important to remember, we do inspections because we don't trust our current model. If our model was perfect, there would be no inspection. So inspection is our best opportunity to check the quality of our model. Every time we perform inspection, we have the chance to improve our model. And we only have the view of robots in different spectra. And it's this with this view that we should count on such a task. So one would perform as much inspections as possible, but there is a shortcoming. Who will check this new amount of information? Then comes another technology, which often sees distance to make help this calibration of a train. It is computer vision. Computer vision has already a lot of applications that relate to twins. We can already detect and measure corrosion, like this picture. We can already measure volumes of elements such as anodes, these points. We already identify and measure torsion in pipes. And all of this information we can use to calibrate the models. This data for computer vision may be entering the same set of data thrown into the wind. that we failed to take advantage in our digital twin models. It is worth reflecting. Is our twin model blind without these images? And not only does the twin benefit from this, our other aspects that seen in our twin model can indicate where there is inconsistency in our AI vision detection. Let's take an example. One of the most catastrophic underwater pipeline accidents is the rise and fall, which we affectionately call the fallout, instead of pullout. As a rule of thumb, first we have a leak in the outer wrap. The water reaches its wires, they corrode, and after some corrosion, they break, and finally the riser falls. Then, with the development of spiral connector in the motor system, we start to have tension sensors on the wires that feed our twin and sense very well when our riser is not safe anymore. The leak that becomes before corrosion usually comes from a puncture that is often visible in inspections. What made us reach this stage of stream through the sensors device stream that corrosion is advanced and we haven't seen the puncture before cover. Then we go to VAR, like in the soccer field. We review the image, and there was our hole. This means also inspection did not perform well. What is the lesson in that? Technologies don't make sense in isolation. In the end, the question is not whether we will make a digital twin, whether we will use IoT, whether we will use neural network. The point that the development of these solutions is always connected to varying degrees. It is useless to think about these decision tools as isolated fields. And we will lose a lot of value in our solutions if we are not able to see the mutually advantage between them. So, so uh, the conclusion is both computer vision is our ally to make better digital twins, and digital twins make computer vision better. So I would like to thank you for the opportunity. You may find me at LinkedIn by putting your community QR code or searching for this profile. No? Should we proceed to the questions?
Thank you very much, Robert. That was brilliant. I love the intricate detail you explained about the subsea automation systems as well. And I would like to ask, even though we're sort of pressing on time, I would like to ask a couple of questions if possible. If, you know, this is my opinion, if computer vision can detect corrosion and other features already, why can't we simply use those models directly to subsea systems?
Well, first, to use computer vision, one must teach the machine to spot the feature we interested on. Right? This requires a lot of examples of the subjects. We want to see corrosion, so a lot of corrosion must be seen. And most of current corrosion models are taken on surface. But when we transport that to subsea, the ROV vision is different. The media is different because it's more bluish. The signal suffers some attenuation. So, how do the techniques of machine learning work very well? We have to train our system again with those new images that are more bluish, ROV image, so it can detect correctly. If you don't do this, it won't detect correctly. So it's the same problem to have Wi-Fi underwater.
Ah,
Water is
good
opaque to
analogy.
Wi-Fi. Water is opaque to Wi-Fi under sea, just like some colors and some other signals we have underwater. So we have to just shift a bit the image to train, and we can use.
I like the analogy there. That was, I think that's nicely explained. Very good analogy about the Wi-Fi. Um, I mean, look, people have been using Robert, subsea systems since the 80s. Probably even a little bit before that. So, isn't this enough data to calibrate the models? What stops this history to be sort of appraised? Because we have that already there.
Well, first, digital twins is something after the 2000s, right? So before that, we didn't have the storage ways, that we didn't have structure to dig this all this information back to the original state. We only have some reports. We only have so the original data, which would be useful to calibrate this model of digital twin, is dug away. And second, when dealing with subsea systems, in the 80s, we were at water depths of 100, 2,000 meters
Mm.
at most. Currently, we are over 2.5 kilometers. And when we stepped through all this depth, there were new challenges. First, the collapse of the tubes, then the fatigued wires. And
Yeah.
every time we took a step further or deeper, it we had a new challenge. So if there is a new model failure, all the information about it is new. Our latest challenge has been stress crash corrosion from carbon dioxide, which we have in pre-salt. So for these modes of failure that are newer, the history is never. So we can regard information from the 80s.